Welcome everybody to lecture number 4 of antenna course. This lecture will be about linear wire antennas. Wire antennas are like the most or like the earliest antennas to show up in science, and wire antennas would have like multiple shapes like this one, or like the loop wire antenna or the helix wire antenna, but we'll be focusing in this lecture about linear wire antennas only, as an example of how to handle and manipulate and analyze wire antennas. They are the simplest but still used in many applications. Also, one note about this is the usage of wire antenna increased with the introduction of PCB antennas. So as we discussed last time, the procedure to find the radiated field from any antenna is either directly through the integration of dE and dH based on their relation to the sources, the real source J, the current source, electric current source, and the equivalent or imaginary source, the magnetic current source, or doing it indirectly through the auxiliary function or the vector potentials A and F. In this analysis, we'll take the second approach where we find A, and here we don't have F because there is no equivalent magnetic current. So we'll find A. From A we'll find H and E. So we're going to start our analysis by looking into infinitesimally small dipole. So a dipole that is really short, so it's just a differential element. Once we do the analysis for this, we can use this information to find to do the analysis for arbitrary long or arbitrary shape wire antennas. So infinitesimal dipole, the length is much smaller compared to the wavelength, because what really matters in microwave and RF is the electrical length, the ratio between the physical length and the wavelength. So it's the ratio of L over lambda is the one that is defined if this is a short antenna, very short antenna, or a large antenna. So it's large and small is always relative to the wavelength. So the first setup that we're going to analyze is having an infinitesimally small element centered at the origin, oriented along the z-axis. And as we know, R is large, capital R is the distance or the vector from source to observation. Small r is the vector from origin to the observation point. So it's the position vector of the observation point. R prime is the position vector of the source. So in this case, we have just infinitesimally short antenna at the origin. So R equal R capital and R small are almost the same, because R prime, which is R small prime, which is the position vector of the source element, is 0, because the source element is very small and at the origin. So just writing the expression for A, the auxiliary function, the vector potential A, as a function of source. Here the source is a linear current, and we have this equation. In this equation, as I said, R capital is approximately equal R small, because R prime is approximately equal 0. We just substitute and we are ready to integrate. So just do the integration and we'll get this expression for A, which is expected. A is always in the direction of the current. The current is infinitesimally small, so integration with respect to dl prime equal the length of this infinitesimal dipole. So L here is very small. In order to find the radiated field, it is always the radiated field is best reported and expressed in spherical coordinate system. So in this case, we need just to do a transformation of A into a spherical coordinate system to continue our analysis. We here just doing the transformation from Cartesian to spherical. We have AX equals 0, AX equals 0, AY equals 0. We just have AZ. So this is 0, this is 0. We just have this element here, and AZ does have this expression because the whole value of A is in the direction of AZ. We just do the conversion. We'll find that AR equal AZ cosine theta. So it has this expression A theta equal minus AZ sine theta, which have this expression, and I hope that everybody knows how to do the transformation. This is sort of like basic information from vector algebra dealing with different coordinate system. And as I said in the introductory lecture, that we need to be fluent into this topics. And A phi equal 0. So we have the three expressions for AR, A theta, A phi. To find H, the magnetic electric field intensity, we just find the curl. Here the curl is in the spherical coordinate system. We'll find that we have just dependency on theta and R. So just do the math and we'll find that HR equals 0, H theta equals 0, and H phi does have this expression. So I'm not going to spend much time into like the math because it's just like a straightforward application of the curl operator in spherical coordinate system. But of course, like you need to do this derivation by hand so that you follow and make sure that you know how to move from one step to the next. Electric field expression, as we did in previous lecture, does have this form. We just apply to find ER and E theta. And here we notice that this is depending on R squared. We're going to talk about this shortly. And we have this expression for E theta, while E phi equals 0. So now the total fields for infinitesimally small dipole antenna, ER, E theta, H phi. So we have 3 components that is non-zero and 3 components that are zeros. So here we need to start like analyze the property of this infinitesimally small dipole antenna. We need to find the input resistance, like for the easiest antenna, a lossless one, and to find the radiation resistance and input resistance for an antenna, we need to find the Poynting vector or the power density vector, then calculate the total radiation power, and then relate this to the radiation resistance, as we like discussed last lecture about the definition of radiation resistance. So we need to find the expression for Poynting vector, then finding the total radiation field, then start to do the analysis. Many analysis is based on this. Calculating the directivity, calculating the effective area, calculating the resistance, as we're going to see, all depending on finding the Poynting vector and total radiated power. Okay, so the W, the radiation density, power radiation density, does have this expression as we said before, and this is the average over time expression of radiation power density. Just doing the math, we'll find that we have this expression, a component of power radiating along R, another component radiating along theta, and the direction is very important of those components, and we're going to do some quick discussion on that. So writing each component alone, because we're going to do analysis on this. WR depending on R square, so one term depending on R square, 1 over R square. The other term depends on 1 over R to the power 5. It has a real term and it has an imaginary term. So the real radiation is related always to the real part. The imaginary part, as we're going to explain shortly, is sort of like a reactive stored energy. Reactive stored energy means it's an electric or magnetic field that is stored, and it is changing its nature from electric stored energy to magnetic stored energy, back and forth. Omega theta here, it's all imaginary. It's depending on 1 over R cubed, another term depending on 1 over R to the power 5. Okay, so this is imaginary power, which means it's a reactive power. It's similar to the power in coil or power in capacitor. It is just stored and changing from one form to the other over time, but it doesn't propagate or doesn't radiate. So here it's just like a qualitative description for the behavior of power. We have omega theta, it's purely imaginary, and for a small value, it's depending on 1 over R to the power 5. So when KR is really small, this is the dominant. It's also the imaginary part of omega R. It depends on 1 over R5. So it is dominating and it is reactive. So in the very small volume around the antenna, the dominant power is the reactive power, or the imaginary part of the power, which is sort of like a stored electric and magnetic energy that exchanges its nature from electric to magnetic back and forth. Once the dimensions increase, once we go like far from the antenna, 1 over R to the power 5 will decay very, very fast, and the 1 over R squared, which is the real part of omega R, will start to increase and dominate. And when we go far in the far field, like 1 over R5 will vanish with respect to 1 over R squared, and we have the radiated power out of the antenna. And of course, this is the real part of the power density vector. As I said, in order to calculate directivity or radiation resistance or input resistance, we need to calculate the total radiated power. So for total radiated power, we integrate over like a surface of a sphere over the whole surface. We just apply this expressions for WR, the one in R direction, W theta, the one in theta direction, over the whole volume, and we're gonna get power to have like this expression, one reactive component that is depending on 1 over R cubed, and the other one is constant, which means the real part is constant. So the total radiated power, when we go at like very large or very small, it's the same amount. So we're assuming here, of course, that it's a lossless media. So this is the meaning. Once we go out of the near field, we have just the radiated power, and the radiated power is just going out more and more and spreading over like larger and larger sphere, while the stored energy or the reactive energy is very large, or the dominant in the area next to the antenna, but it is decaying very fast as a 1 over r cubed as we go away from the antenna till it vanishes. So when we go in the far field, we can say, okay, we don't have any reactive energy and or no reactive power. We only have radiated power. So the radiated power, as I said, the total like power density is resulting in radiated power and stored power that goes between like magnetic and electric forms. It is called like reactive power and or stored power. Okay, so the radiated power does have this expression, and the reactive power does have this expression, and as I said, it decreases very fast once we go away from the antenna. So the radiated power is related to the radiation resistance with this expression, and from here we can find the expression for radiation resistance. And remember, this is for infinitesimally short dipole or infinitesimal dipole. Infinitesimal dipole means that L over lambda is less than 1 over 50, so it's almost a differential element. And in this case, the radiation resistance does have this value, 80 pi square multiplied by L over lambda square. And of course, this is very small resistance because this is like L over lambda is really small. So in order to find the radiation pattern or directivity or other terms, we are writing ER and E theta and E phi again, just to remember. And now we look into this in the far field. So in the far field, we have ER is depending on r square and 1 over r square and 1 over r cubed. E theta depends on 1 over r, 1 over r square, 1 over r cubed. H phi depends on 1 over r, 1 over r square. And in the far field, we can neglect any higher order with respect to 1 over r. So all the r square terms and higher, 1 over r square and 1 over r cubed and so on and so forth, will vanish in the far field, leaving only the terms that's depending on 1 over r. So the whole ER in the far field is negligible. The 1 over j and 1 over k square component of E theta also will vanish in the far field, leaving only one term that's depending on 1 over r. Same thing for H phi, only one term remains, the other term will vanish in the far field. So the far field expression, ER will vanish, the other three components are already zero, and we are left only with E theta and H phi. The ratio between them follows the laws for transverse electromagnetic wave. So the wave in the far field is pure transverse electromagnetics, and the ratio between theta and phi equals the wave impedance, which is the intrinsic impedance in this case. So we can write W radiation, which is E theta and E phi, in the far field we can just neglect E5 because it is like negligible with respect to theta, as we just said, and we have the expression for B radiation, the total radiated power, so we can calculate the directivity, which is 4 pi over total radiated power multiplied by the power intensity value, and maximum, we just find the maximum of the power intensity and substitute in the formula. So doing that, the radiated power, which is average over time, would have this expression. So it has dependency on theta square, and the maximum is when theta square equal 1, and this happens when we have like this expression, and we find that this the ratio, the maximum, equal 3/2. So the maximum directivity of infinitesimally small or like short dipole antenna is 1.5, which is equivalent to 1.76 dB. The normalized with respect to unity, normalized power intensity expression is sine square theta. Radiation resistance does have this expression. From directivity we can find the maximum effective area or aperture of the antenna, which is lambda square over 4 pi multiplied by maximum directivity. So once we have the radiated field, we can use this to find all the antenna parameters as the exercise that we have in homework number 1. So if we draw the radiation pattern for this infinitesimally short dipole, we'll find that it's omnidirectional. In the phi it is uniform, but it has the sine square theta in the theta direction or in the elevation. So in azimuthal it is uniform, in elevation it is sine square theta. So the other, now we are ready to do the analysis for arbitrary length dipole, but as a special case we're gonna handle first the small dipole because it gives us some important information. We can just jump to arbitrary length, the difference is a little. So the main idea here when we go from infinitesimally small to arbitrary length or to short is the current distribution. So what will be the current distribution on the two arms of the dipole? So the idea here is that the the current distribution on the arms of dipoles is it's exactly the same as the current distribution on the two wires of parallel wire transmission line in the open circuit case. So if you think of those two lines as, let me do this. So let us think as if this length was just extending like this. So it's an open circuit transmission line. So if we have an open circuit transmission line, what will happen? We'll have the current equal 0 here, and we can find the expression. So this is exactly the same or like the best approximation for the current distribution along a transmission line. So we think of the current as the current distribution over an open circuit parallel wire transmission line. Then this arm is extended, or like, sorry, it's turned to be this one, and this arm is turned to be that one. When the length of the dipole is not infinitesimal but very short, we'll have like a small portion of a sinusoidal current distribution. When it is a little bit longer, so we'll see larger portion of the sinusoidal curve. When it's longer, so when it's lambda over 2, we'll have like the current distribution 1/4 of a sine wave current distribution, or like a sine function current distribution, and another quarter. When we go at longer length, we'll see more portion of the sine function, and we might have, when we go like larger length, or like when we go for taller length of the dipole, we will see like multiple part, and we'll start to see here the current here is positive, the current here is negative, but we draw it this way. We can also draw it that way. So this curve here, sometimes we draw it, okay, we can also like draw this as, okay, sometimes we can also like draw it this way. So it's either draw it like on this red curve or the blue curve with sign indicated here. Okay, so when the length is larger than lambda, we'll start to see like a positive half of a sine function, then we start to see part of the negative half, so on and so forth. So the current distribution is something crucial, because this is used for the calculation of the radiated field. So here it's the same shape that we are familiar with, or the same like coordinate systems that we are familiar with, but now we have a distribution for the current on the arms of the dipole. So we take just an element here, the length of the element is dz prime, its position is, the position function is z prime in the direction of az, and we'll do our analysis based on that. When we're dealing with like short dipole, the general expression, the more accurate expression, is to write the current distribution as a part of a sine function. The expression of the sine function on the top arm is this form. The expression of the sine function on the bottom arm is this expression. And this expression is valid for any length. It's not just for short dipole. For short dipole, this function here is short because L is small, sorry, Z prime is small, or like L over lambda is very small. So this expression here will be small, and we can take this approximation, sine x equal x. So the function, the current distribution of this dotted curve at short dipole actually can be approximated as like a triangular current distribution. So this is the assumption here, or like this is the approximation here. We can use it, and it will give us the same value as this one, but I'm not gonna do the approximation. I'm gonna just use this one because it's more general, and also it can be reused when we have longer length dipole antenna. So the two approaches exist, but we're going to take the first one. So here, the expression, we also have AZ, we have the current distribution, but now we have two different approximation as we discussed in previous lecture. The term for amplitude, we can approximate R to equal like certain like R equal R, but for the red term in the phase, because the phase is more sensitive and periodic, we'll have like more accurate approximation, and this approximation is R capital equal R small minus R small prime, which we did this approximation before in previous lecture. And when we put r prime, which is the position vector of the observation point, and r prime is the position vector of the source, ar is the unit vector along the direction of the observation point, which is arbitrary point in spherical coordinate system, which is ar. Just doing this, we'll find the expression for approximation for r capital in the phase term to have this expression. This is the general one, because we might also like have the dipole oriented along different direction. So if we just have a different direction, this r prime will be along the direction of the antenna, and this ar is always the position vector of any arbitrary point in spherical, so it's always ar. So now the az would have this expression integrating from minus L over 2 to L over 2. The current distribution here is not constant, it's a function of position, and this is the expression on the upper arm, on the lower arm. So the integration here will be just decomposed into two components. Like dE theta and dE r and dE phi, we can take it from like slide number 20. And in this expression, we do the same approximation for r capital in the phase term and for r capital in the amplitude term. So now we like calculated A, and we know that A will produce like E, so we can integrate also. Now we can integrate E that we already got before. It's the same thing, but now when we do this approach, we just bypass the curl expression, because we did the curl on the dA, so we get dE and dH. So we do like just the integration without any need for a curl in this analysis. So we have dE theta with this expression, and now we need to integrate this from minus L over 2 to plus L over 2. So we can take this term, it's called the element factor, and when we study the antenna arrays, we'll know the benefit of having this just terminology. But now let us just go on. When we study the antenna array, please like come back to this one, and it will make a better sense for you. Okay, so as I said, the integration need to be divided into two parts, for the lower arm and for the upper arm, and we need to do those two integration. The integration is related to this like Bayer identity, where alpha equal jk cosine theta and beta equal plus or minus k, depending the plus or minus is for lower arm or upper arm. So this is just a closed form, but doing the expression, we'll find that E theta does have this form. Okay, so this is very important. You can even memorize it, or like you don't need in the exam, but this is very handy expression that is used to find many properties of wire antenna. So this is the field pattern. When we normalize to this common factor here, this will be the field pattern. If we are to draw the radiation pattern, the radiation field pattern, we're going to use this one. If we need to draw the power radiation pattern, we use the square of this term here. And so far we didn't like do any approximation in the current distribution, so this derivation here is applicable for arbitrary lengths. Now, in order to calculate the properties and parameters of the antenna, we need to calculate the radiation pattern, the radiation resistance. So we need to find the radiated power. So the radiated power here, again we're dealing with the far field only. So the radiated field is as expected is in the AR direction. It does have this expression, and as I said, it's the square of E in the far field. So this is the expression for radiated field. The power intensity is just multiplying this by R square. So it's certain parameter multiplied by this expression square. And if we want to draw the radiation pattern in the elevation plane, because here again in the azimuthal we have like uniform, there is no dependency on phi. So here it is showing the radiation pattern for a number of lengths. For very short dipole, infinitesimal dipole, it is this wide. The longer we go, the more pointing and more directive the antenna gonna be. And we stopped here at 1 L equal lambda, as we're gonna see what is the reason. And from this pattern we can calculate the half power beam width. So the beam width between null here will equal pi. So because this is the first null, so the whole, we just have one loop. The half power beam width for different lengths can be found from like the 3 dB point in the radiation pattern. And as we're gonna see, or as we see here, the longer the antenna, the more directive it's gonna be. When we go for lengths larger than lambda, we start to see secondary loops or side loops. Yes, the antenna is becoming more directive, but the power is oriented in like more loops, and also the field of course switch its direction after the main loop. So this is the same thing in 2D. So the radiated power, we know the expression how to find the total radiated power. To find the radiation resistance, it is related to the radiated power with this expression as we discussed last time. For directivity, the radiation pattern of the dipole becomes more directive as the length increased, but when the length exceeds 1 lambda, we start to see side loops. So the directivity, again, it's just like now we are going into some sort of like application of the definitions of the antenna parameters. And here we are showing a number of curves for maximum directivity, for radiation resistance, for input resistance as a function of dipole length. And it's part of the homework. The next homework that's going to be given next week is to regenerate this curve using a MATLAB routine from the formulas that we had just discussed. So the radiation resistance is related to the radiated power with this expression, and input resistance is related also to the radiated power with this expression here. So I input is the input at z prime equals 0, so at the input of the dipole, while I naught is the maximum current on the whole distribution. So I naught is the maximum current, In is the current at the input of the dipole antenna. And if you notice here, So for value of lambda below 0.5, the two curves are, where is this? So this, okay, so this is Rn and this is R radiation, and they are the same up to this value, up to lambda over 2, and after that they start to like depart. And you can think about this. Why is that? Think about that. Also, like our input can reach infinity because, like for example here, when we are at L equal lambda, we'll have, as we saw here, when L equal lambda, we'll have this point here equal 0. So this is like 1/2 wavelength, this is 1/2 wavelength, so it will be like one complete half cycle of sine here. So I input will equal 0, and when I input equals 0, the radiation resistance will go to infinity, as we see here, while our radiation never goes that high. So those are just like the expressions. Okay, and here like some points to just read, and I marked this as for your information about like how to analyze the dipole antenna, because when we're dealing with dipole antenna, we're assuming it's like a wire without thickness, and we are neglecting what is happening at the feed gap, the separation between the two arms at the input of the antenna, and those two things affects the performance of real antennas. So here some discussion about this, and also like you will have an assignment on that also like give you some practice on this. So please read those terms or like those slides, and we're gonna exercise them in an assignment. I'm gonna stop this lecture here and continue the next part for next week, inshallah. Okay, assalamu alaikum everybody.